afternoon, my dear students. So, in this session, I will going to discuss the concept of single cantilever and how to derive the expression for the depression produced by a cantilever. So first of all, let us understood the meaning of single cantilever. So, what is a cantilever? Cantilever is a beam whose one end is fixed, the other end is loaded. So, such an arrangement is called cantilever. So, in order to derive the expression for this depression produced by a cantilever, so we have to consider the diagram of a cantilever. So, as I have already said that cantilever is a beam fixed horizontally at one end and loaded at the other end. So, this arrangement is what is known as cantilever. So, cantilever, single cantilever, both are same. Don't be under the confusion that cantilever is different and single cantilever is different. So, then the Young's modulus of the material of the cantilever can be determined using the value of depression produced in that cantilever. So, in order to determine the Young's modulus of the given material of the cantilever, so that can be determined by using the value of depression produced in that cantilever. So, now the experimental arrangement is made like this. So let OA be a cantilever of length L fixed at O and loaded with a weight W at the other end of the cantilever. Let AA dash is equal to Y, that is the depression at the free end. Consider an element of length PQ of the beam. Consider an element PQ of the beam of length dx at a distance x from the loaded end. I think it is clear to you now. C is the center of curvature of the element PQ, where C is the center of curvature of the element PQ, and capital R is the radius of curvature, and capital R is the radius of curvature. So, the weight W at the free end A and the force of reaction W at Q, which constitute the external couple, so that the external bending moment value will be equal to W into X. What is W? W is nothing but the weight which we have kept at the free end of the cantilever, which we have loaded at the free end of the cantilever, and X is the distance. So, thus the internal bending moment expression is given by the equation QAK square divided by R. So, this expression we have already derived when I was discussing about the bending of beams and how to derive the expression for the bending moment. So, we have derived this expression and this expression is known to you already. So, at equilibrium or for equilibrium, so this external bending moment, that value will be equal to the internal bending moment. So that we can write WX will be equal to QAK square divided by R. So, these two mathematical expressions which represents the external bending moment is equal to the internal bending moment for equilibrium. So, using this equation, we can derive the expression for the radius of curvature as capital R will be equal to QAK square divided by W into X. You call this as equation number 1. So, now what we should do is we have to draw the tangents at the points P and Q meeting the vertical line at T and S. Thus, Ts will be equal to dy. So, dy represents the small depression value. dy represents the small depression value for a small load, and an angle between these two tangents that will be equal to d theta. So that will represented as PCO. Hence, so PQ will be equal to dx. It is as good as r into d theta, where r is the radius of curvature of the bent beam. So then d theta can be written as Wx dx divided by Qak square. So this we have written using the relation 1. This equation I have written using the relation 1. So from the figure we can write the small depression value as dy will be equal to x into d theta. So then dy can be written as Wx square dx divided by Qak square. So then now our aim is we have to derive the expression for the total depression produced by a cantilever at the free end. Therefore, the total depression at the free end of a cantilever is given by, so that can be obtained by integrating dy expression between the limits 0 to L. So then integral of y dy becomes y, as we all know, because we know the integration better than me, because we have studied integration at your secondary school level, and also we have studied at second PUC you have almost all you have studied integration as well as differentiation. But so after integrating this equation between the limit 0 to L, so you will get the expression for y as W into L cube divided by 3QAK square. That will be equal to, again, y becomes mgl cube divided by 3QAK square. What is W? W is nothing but mg. Therefore, now, so this is the equation which represents the depression produced by a cantilever. So in order to determine the Young's modulus of the given cantilever, so you just by altering this equation we can write Q is equal to 4mg L cube divided by B d cube into y. So this is the expression which represents the Young's modulus of the cantilever for rectangular cross section of the beam. So if the beam is of rectangular cross section, so this formula holds good. So sometimes if they ask you to write the expression for Young's modulus for a circular cross section, so in that case you are supposed to write Q is equal to 4mg L cube divided by 3 pi r to the power of 4 into y. So the general expression is 4mg L cube divided by its geometrical moment of inertia. If you want the expression for different cross sections, so then the only thing is you have to write their concerned geometrical moment of inertia formula. So thereby you will getting the expression for the Young's modulus for rectangular cross section and also for the circular cross section. So this concludes today's session. I hope that you have all understood this in a better manner, and you can understand even the same concepts even in practicals also, because we will have this experiment in this semester. So there also we will going to discuss in detail. There you will be conducting the experiment on your own. So thereby also you can acquire lot of knowledge about this experiment. Thank you.